Hi, good evening. Welcome to the third day of Java Webinar Week, brought to you by Spartans with a huge help from our friends at JustJohn IT. My name is Michał Michalczuk. I'm a senior software engineer in Spartans, but today I'm your host. Yesterday we've heard, Olivier. Okay. Sorry guys, but someone have audio on, maybe Przemek. Okay, never happened. Sorry about that. Okay, so yesterday we've heard few words about performance, and today we also dig into it with topic Who Collects Your Garbage by Przemysław Bruski. A few words about Przemek. Przemek is currently working on making Atlassian Data Center products scale better, and over time he worked on many products in various technologies ranging from Linux kernels and drivers to JEE SOAed apps. He loves agility of small teams and hates the interior of large teams. I can relate to that totally. And if you have any questions during the webinar, please write them in the chat, whatever you're watching that on Facebook or on YouTube. We'll pick them up and have a small Q&A session at the end of our event. It will take about 20 minutes. Please watch for the unexpected slides on today's presentation. I hope you know why. And that's all from me. The stage is yours, Przemek. And we see each other after the presentation on the Q&A session.
Thank you, Michał. Hello, let me introduce myself again. I'm Przemek. I'm an architect working at Spartans. Today I'll be talking about garbage collection, performance related to garbage collection. We'll be doing some measurements on live application. I've chosen Jira, obviously. And we'll be looking at various garbage collectors available to you in Java VM. So my hope that your takeaway from this will be some idea on how garbage collectors work, which garbage collectors are available, how to choose them, things like that. So let's get on with it. Let's start off by looking at what's happening when we actually call new object in Java, because we'll be talking about Java garbage collectors. That memory, obviously that object has to be backed by some memory, which has to be allocated, potentially later reclaimed, and potentially returned to the operating system. So these are actually the tasks that garbage collector does. It handles memory allocation, and it must do it because otherwise you will have no memory to work with. May handle memory reclamation. That may be surprising. If you look at the name, garbage collector, it should sounds like it should collect the memory, but maybe not necessarily allocate it, but actually it's the other way around. And it also may return memory to the operating system, depending on garbage collector operating system and the settings. So how many garbage collectors are there? I'm sure you've heard about a couple. I was really surprised by the actual numbers. Java 8 has 6 garbage collectors available to you to choose from. Java 14 has 7. They've added garbage collectors and also removed. And this is just talking about the main line. You can obviously have builds of Java that have more garbage collectors, which is kind of surprising. Why do we have that many garbage collectors? This is actually, you can only have one active garbage collector at a time, so you have to choose one, but it's also only partially true. You will see later on that there are some cases where you are sort of running 2 garbage collectors at the same time. So why do we have that many? The reason is that behind it is that collectors have goals, and these goals can be different. Typical goals include pause time, throughput, and heap footprint. Pause time is simplest to explain. Garbage collector sometimes has to pause the application to perform collection. Throughput is slightly more difficult. It's basically the ratio between the time spent on garbage collection and the application time. So that reflects the amount of time that garbage collector stole away from your application to perform the collection. And the final goal is heap footprint. So that's the actual amount of memory that the JVM will request from the operating system to allocate as heap. This can grow or shrink depending on, or remain stable depending on the garbage collector and settings. So how are these goals selected? Obviously, as you know, in life, you can't have a cookie and eat the cookie. So you have to select some of the goals. Some of the algorithms that we'll look at today are goal-oriented. I will mention which goals are behind the algorithm of each of the garbage collectors. Then they also have priorities. So some garbage collectors, for example, optimize the post time, but if this goal is met, then they'll start focusing on the throughput. And if this goal is also met, then they will also have a look at the heap footprint and optimize that. If any of the goals is not met, they will not proceed with the subsequent goals. Also, you can tune these goals a bit or say how your personal priorities look like. But again, that depends on specific garbage collector algorithm. And there is some heuristics and automatic tuning happening, again, depending on the garbage collector which you're using. So let's take a look at our first garbage collector. This is actually a super popular garbage collector that probably very few of you heard about. That's EpsilonGC. EpsilonGC is available in pretty much every single JVM available right now. It's high throughput, has minimal latency, minimal overhead, and handles only memory allocation. So in other words, it doesn't handle deallocation at all. Whatever you allocate stays there forever, and eventually, if you don't have a heap of large enough size, you will run out of memory and your JVM will crash. So why would we have this garbage collector at all? It's primarily for testing, because if you want to test some algorithm and don't want to be influenced by garbage collection, you just run using Epsilon and see whether how your algorithm performs. And I guess the lesson learned here is be careful what you wish for. That's a garbage collector you definitely don't want to use in production, but it looks really good on paper. So in real life, you will have to choose between these goals, between your priorities, because otherwise, for example, Jira would die within minutes of startup, even with a really large heap. Okay, so let's have a look at more realistic cases of garbage collectors. So that's SerialGC. That's one of the older garbage collectors. It's been actually the default setting in Java 5 and 6, and for lower end machines, it was chosen for version 7 and 8 as well. It's serial, so there's no concurrency or parallelism involved. Why would we even run it nowadays? On embedded hardware, when you have a single core, obviously running something in parallel doesn't make that much sense. And also, if you're running multiple JVMs on a single machine, they would compete for resources. So it might make sense to have, let's say, 6 JVMs, each running single-threaded serial garbage collection. It's a mark and copy for young, mark, sweep, and compact for old generation. I will explain these terms, briefly explain these terms in a second. We are not testing this SerialGC because so in this presentation, I will not show any performance results from VGC because I don't expect that anyone is running Jira on embedded hardware, so that's not a realistic scenario. Okay, so I promised to explain this mark, sweep, copy, compact stuff. First, let's start with mark. Mark is a part of garbage collection where the garbage collector is trying to determine the live objects, the objects that are accessible and should not be removed. This is done by doing a depth-first search from so-called GC roots, which are all the references to the objects that JVM keeps, and they have to be live. So whatever is connected to them will be live as well. Sweep is the phase of garbage collection that releases memory of that object. So if that object is unreachable or dead, we can release that memory. Compact is an optional operation. Some GCs don't do that. That basically moves the object around within heap to avoid fragmentation, because otherwise you would end up with holes where you deallocated the memory, and then it would be more and more problematic to work with such heap. Finally, we have a copy, which is a bit similar concept. You copy to a new place in heap, not within the same region, but new place. Okay, so let's have a look at ParallelGC and ParallelGC. Now, again, we have a case of a bit misleading name. It's not ParallelGC and an old version of ParallelGC algorithm. It's actually a similar algorithm which treats the old generation, and I will explain generations in a moment, differently. The goal of this garbage collector is to optimize throughput, and you have to accept longer pauses. It's also quite old. It's been available since Java 1.4, and it's been made default for Java 7 and 8. It's still available. It's actually pretty good. So it's parallel on young generation and optionally parallel on old. So depending on which flavor you choose, it will be either parallel on old, parallel on young, or both on both. I will explain what that actually means in a second. The reason why we have these two approaches to young, different approaches to young and old, and you will see similar split in other garbage collectors as well, is that these two generations have really very much different characteristics in terms of how many objects are created there, how many objects die very soon, and so on. So what does this parallel and concurrent mean? Parallel basically means multi-threaded. So if a garbage collector uses multiple threads, it's considered to be parallel. If it's concurrent, it means it runs concurrent or mostly concurrent. It runs concurrently with the application, right? So it steals away some performance from the application, and at the same time, once it kicks in and starts to collect garbage, it obviously will have some work done beforehand concurrently with the application, so the pulse should be smaller. Now I also promised to say something about generations. So just a brief primer. Generally, you have that depends. Oh, sorry, that's a bit of a mistake on the slide. But how these generations are treated and what exactly is in them depends on the actual algorithm. Generally, we have old and young generation, and within them we have some spaces such as Eden, Survival, Tenured. I won't go into details here, but it's important to remember that some garbage collectors do rely on the fact that some of the objects are older, some of them are younger, and treat them differently. And these are called the generational algorithms. The sizes of these generations, because obviously they are kept on heap, or they're part of the heap, are configurable, and also some garbage collectors tune them on the fly. Again, depending on some settings that you supply to them. Okay, so we know so much about the GCs now. Let's maybe test our first garbage collector, do a bit of a performance test. But before that, we need to look at the setup. So, as I said before, I will be testing using Jira on two rather beefy machines. So each of them has 36 virtual CPUs, 72 gigs of RAM, and is based on NVMe disks. So these are solid state disks, really fast. I'm also using 40 gigabytes of heap, and I disabled uncommit. Basically, the way you do it is you set minimum size of the heap equal to maximum size. That means that heap won't shrink during garbage collection, and that memory won't be returned to operating system. I consider that to be an overhead that we don't really need in our performance testing. Your mileage may vary. The version of Java that we'll be using will be Java 11, a version that is distributed by a guy called Alexei Shipilov, who works for Red Hat and works in one of the next generation garbage collectors. And I also cross-checked that with Java 11 Corretto. Corretto is the distribution of OpenJDK handled by Amazon, and is available on Amazon Linux. because I used Amazon Linux 2 to test with kernel 4.14. That's an important detail because of a feature called huge or large pages that I will discuss a bit later. Okay, the other component of my testing will be a tool called JPT. That's Java Performance Toolkit. It's an Atlassian-made performance measure tool. It's used to measure performance of Jira. It's capable of provisioning a whole Jira cluster with a single line of code, and that includes the necessary software, the data set, and the hardware. The data set that we'll be using is rather huge. It's been modeled on production system of one of the big database vendors. It also applies load on that cluster, and also stress load. So the load is configurable. Today we'll be using stress load. So basically we'll be throwing load at the system as fast as possible. JPT also collects data, so that will, it will provide us with the data that I will later show you on graphs. And it's WebDriver based, in case you were wondering was it underlying technology. It's a bit unpopular technology in the performance world, but that's what we used. And feel free to ask more about it in the Q&A. It's a large topic and I don't want to consume time for that. Okay, so this is the result. I will briefly, this is the only one that I will go into detail with because I will later show you a summary of all the runs that I've done. So let's use this as a model. This is a timeline graph, right? So times go here from left to right. The yellow line at the bottom is the amount of users. As you can see, it slowly grows. There's a ramp-up time. Then we have a steady amount of users, and then they gradually log out of the system. The reddish line is the amount of actions performed within a time stamp of a minute. As you can see, it again gradually builds up. This is related to two things. In this case, you can see that something wrong happened with garbage collection. On the other part is the line on the graph, which is the mean latency. So there has been some delay, and at some point, only after some time, the collector or the Jira reached maximum throughput, and then it remained quite flat throughout the test. The response time graph, so that that's the greenish part, is again quite flat after some initial period of something wrong, which we don't really know. I don't really know what happened. I can only assume that self-tuning parts of heuristics in ParallelGC kicked in and started adapting to the load more properly, and that's why we ended up with this flat section later, which is actually good. We can also have a look at a more detailed view of what was happening underneath. So these graphs don't come from JPT anymore. This is the pause graph. So as you can see, at the top you have longest pauses within a time span of 10 seconds, and at the bottom you have a sum. So it looks like it was pausing for a quarter of a second within roughly 10-second time span, which is actually a pretty good result. We'll compare it with G1 and only G1 because it does take us a long time to compare it with all the garbage collectors. But keep in mind, quarter of a second per 10 seconds is actually a pretty good result. The other thing that I want to show you is how the heap looked like. So this is a typical CISO profile of garbage collection where you have reached some like 23 gigs and then deallocate memory during garbage collector phase and then go up again and so on and so on and so on. You can also, what is interesting, and again we'll compare it with G1, is that you have a trend here, right? So the memory consumption goes a bit up all the time. Okay, I promised to tell you about huge and large memory pages. I will be testing both with normal or small pages and large memory pages. Typical size of a memory page is 4 kilobytes. That's the default one on Linux. But you can enable bigger ones depending on hardware, operating system, So the typical large page will be 2 megabytes. You can also, I think, enable 1 gigabyte. The reason why we have all these settings is we want to reduce the address mapping penalty. So basically, whenever we want to look up an address, we have to map it to a physical address. It's an expensive operation, so we have a cache, and that cache can become filled quite fast. Once it gets filled, we get into this expensive operation territory. So the idea behind larger pages is that if you have larger pages, you don't need to allocate that memory and enters in the cache, and the whole system goes more smoothly. And we'll see whether that actually held through in our testing. There's also a feature called transparent pages, which sort of work automatically. I wasn't using it for this test. I was using non-transparent, so manual, where you basically have to upfront declare how much memory you want to allocate within this 2 megabytes pages. And typically you need to allocate as much as you have heap plus like 10-15%, so that other applications allocate the memory, and also JVM using this page, using memory allocation for non-heap allocations, actually has these pages available. Okay, so let's continue with another algorithm. And as I promised, I won't be showing you graphs right away. I will just show them right towards the end. Now I'll just go through algorithms available. It's also quite old, available since Java 1.4. Unfortunately, some people really despair. It has been removed. It's no longer available in Java 14, so we won't be testing performance with it. It's one of these hybrid garbage collectors where young generation was collected using ParallelGC, and pure CMS was running on the old generation. The goal was to minimize pauses. And the big drawback of this garbage collector was that it introduced fragmentation to heap. And I guess that's probably one of the reasons why it was eventually removed in Java 14. Another extremely popular garbage collector is G1. It's available since Java 7. It's been made the default garbage collector in Java 9 and up to 14. So I checked out the latest version of Java yesterday. It was still G1 as the default. It's parallel, concurrent, and compacting, so it doesn't fragment heap. And the goal is to have small uniform pauses at high throughput. And we'll be able to see whether it's actually true in a moment. It can also be tuned for higher throughput or lower pauses. So you have some dials, knobs to turn where you can say, okay, I want higher throughput, I want lower pauses, but obviously within certain limits of the main algorithm. So this is how the pauses look like. As you can see, they are not really uniform, I would say. So ParallelGC was a bit more uniform, and also are quite big. So you reach up to 1 second within 10 second per period. So at least the uniformity behavior was a bit better with ParallelGC. What will be interesting to see later on is how that influenced the overall throughput of the application. We can also have a look at the heap. And as you can see, it's a bit different here. So there is no trend, not really, at least in this part of the graph. And it just keeps on going up and down, and then it looks like all memory is reclaimed. So with ParallelGC, it looked like we have a bit of a memory leak. With G1, it looks like maybe it's not a memory leak, but rather a property of how ParallelGC was looking for candidates to reclaim space from. So that's it for the more or less non-experimental or production-ready garbage collectors, obviously apart from the Epsilon, which is probably not, you don't want to use that. We have now some experimental ones. So that's Shenandoah. That looks almost like the magic keyword for today. I've been told that Shenandoah in language of Native Americans may mean something like beautiful daughter of the stars. It's also a name of the river in the US. It's a garbage collector sponsored by Red Hat, so there's a team there working on it. It's available since Java 13. but not in mainline. You can also get it even for Java 8, but again, not in mainline backport. The best way of getting it, if you want to try it out, is to get the distribution from Alexei Shupidov. It's again like many modern GCs, it's parallel concurrent compacting, so no fragmentation issue here. Promises low post time, and post time is less dependent on heap size. So even if you have a really big heap, and I mean really big, supposedly the post times will be quite small. The other, or in similar category, a newcomer to the GC crowd is Z. Z is not 0. Epsilon is 0. Z is just Z. It's Z. It's been available since Java 11, but will only be production ready in Java 15. So take the performance results from both the Shenandoah and Z with a grain of salt. It's a bit of an unfair comparison because we are testing really battle-tested, well-tuned garbage collectors with work that's even by the creators of them considered to be not finished, not production ready. But they're always stable enough to show some performance results. Again, parallel, concurrent, and compacting. Post times do not exceed 10 milliseconds, and they have a goal of not exceeding 1 millisecond, which is awesome. If you compare it with ParallelGC, which was better than G1, if you remember that, 1 millisecond is a very, very ambitious goal. And again, post times should be less dependent on heap or live set size. The creators claim that you can run a heap of up to 1 terabyte, and the performance will not degrade significantly together with the heap growth. Okay, so we went through all the GCs available in your standard JVM. Let's have a look at how they perform under load. So this is the action throughput graph. I will zoom it in a moment, so don't worry that you don't see anything. I actually see very little as well, but I know what to talk about. So this is the ramp-up time at the left side of the graph. So we'll basically ignore that because that's where the virtual users are logging into the system and are not putting a significant load on the system yet. And as you can see, all the GCs, Jira under all GCs levels up a bit, and we'll zoom into that part of the graph. So these are all the available garbage collectors, and look at the difference here. So Shenandoah performed the worst. Shenandoah under small memory pages, so 4K, and the best one was Parallel on 2 megs memory pages. This is actually quite a big difference because that's 1,000 actions per minute. So that should potentially be visible to the users already at this point. The other thing we could look at is response time. Again, I will zoom it in a moment. The response times remained quite flat throughout the test run, except for this spike here. That's ParallelGC doing something. I don't know what. And if we zoom in, the situation is pretty similar. Parallel on 2 meg on large pages remains the fastest, and ZGC remains the slowest. And again, if you look at the actual data here, it's a difference of 1 second. Yeah, no, it's 200 milliseconds. Sorry. So that's again quite significant. Obviously, on this graph, smaller means better. This is a random slide that's not in this presentation, but you may want to make note of that keyword if you want to. And that's really all I had. So if you want to ask me something about how I tested, what hints would you give? Would I give to for performance testers, or how would you test your Jira? Feel free to ask me about it. I'm not a garbage collector expert. I'm just guy running performance testing, and maybe changing some settings such as pages size and things like that. So over to you, Michał. Do you have anything for me?
Hi. Of Of course, I have a few my own questions, and I have a few questions from you, from the audience. If you have some more, please write them in chat, whatever you're on Facebook or YouTube. So I have a good question in general regarding the GC. How your choice of GC impacts the way you write the code?
So that depends. I guess in modern applications, it doesn't really. But if you're working with embedded hardware, if you don't want garbage collector to kick in, if you have to guarantee certain response times and you have to factor in the post times, then obviously you have to budget the time, plan for it. In case of Epsilon, maybe even reuse existing objects, a practice that's generally frowned upon with modern garbage collectors because it doesn't bring any benefit. But with Epsilon, obviously, that would save you. So to answer is really twofold, right? Modern apps, modern web apps, we probably don't care. And with some dedicated, very specific use cases, you need to pay close attention to which garbage collector you choose, why, and what will be the worst case scenario that you'll be facing on production.
So that's a good segue to next question. So what about Jira Server? I will give you some context. Przemek is working on Jira servers, so Jira on-premise, which you can install on your own server. It's not the cloud solution, which we also have. So what about Jira?
So approximately 90% of our customers still use Java 8, and I assume that majority of them uses ParallelGC, which came out at the top in our tests here. The rest uses G1 because they are on Java 11. We are not doing really anything specific to support this. We test the garbage collectors, figure out what's the optimum heap size for stress loads, for really big customers. That's basically the extent of our work with those. While talking about tuning or selecting garbage collectors, it's very important to remember that there could be a penalty, right? In general, G1 was chosen as a default garbage collector because it's probably better for the typical use case. So that doesn't really mean that you should switch to ParallelGC right away. Also important, in my tests, ParallelGC, although in general it came up on top, it did behave a bit erratically, and sometimes actually the performance was the worst of the whole pack. So that was a bit surprising for me as well. Finally, with this tuning, it's really easy to shoot yourself in the foot. Even like with this super simple change of changing the page size from 4K to 2 megs, I encountered some kind of kernel bug where after I shut down Jira, the memory remained allocated, and I had to restart on both nodes because they basically didn't have, all of a sudden 40 gigs of RAM was missing. So
yeah, I wanted to ask that question. How can it break your code? I mean, if you're switching from one GC to another, how we can break your code? Maybe you have some more examples. That's because for me that sounds like the worst case ever, and that's one of the reasons why, for example, banking systems are not migrating to the newer Java versions nor changing their GC implementations because of the risk and the unpredictability. That's my assumption.
Yeah. So in general, it shouldn't break your code. In general, but if you just from the super simple test that we've done with ParallelGC and G1, you've seen the post times go up through the roof, like they quadrupled. So if a system relies on faster response times and all of a sudden you add random 750 milliseconds at some point, it may turn out that it's actually not fulfilling the non-functional requirements placed on it. So that's problem number one. Problem number two is that if you change the garbage collection algorithm, obviously it will consume different amount of resources. If you're lucky, it will be smaller amount of resources. If you're unlucky, it will be higher amount of resources. And also there are some circuit breakers built into garbage collectors where when they start considering that they can no longer cope with the amount of memory thrown at them, so they spend too much time garbage collecting, they stop working and they basically crash your JVM. This is pretty much a corner case scenario where your heap is exhausted and your allocation rate is really, really high. But technically, it could happen that under one garbage collector, your application is stressed and and has low throughput because it spends a lot of time garbage collecting. But under another garbage collector, the garbage collector cannot cope with the amount of allocations and will just crash the JVM. That's, in the first place, your application wasn't in a good place. So it's not like it's a fault of the other garbage collector, but yeah, technically you could blame the garbage collector for that happening.
Okay, I've got a question from Łukasz about using Java in general, but before that, I have a small announcement for you. I saw your messages about our email address, www.spartest.com. I've got the confirmation that it doesn't work at the moment, but we're working on it, and if it won't be able today, it will for sure be able back again tomorrow. So sorry for that. Okay, but backing to questions from the audience, I have a question from Łukasz Wąsowicz. Let me quote it. When memory consumption and fragmentation really matters, is Java still a good choice or it's a suicide?
I don't know. It depends on the use case. So if you, we haven't really looked at the throughput parameter in all these tests, right? But technically, we could have a look at throughput and see how much performance we lost because of garbage collection. I know that it is about 7% in the worst cases, I think. So that's how much performance you lose by relying on garbage collector. The other
7%?
7%.
Okay.
Which probably can be tuned a bit more, and this has been a stress test scenario, so typically it's better. The other trade-off is, okay, so let's say you start managing your memory on your own. I think 2 days ago there was an announcement that 70% of high impact and critical issues in security issues in Chromium come from the fact that memory was mismanaged. So there was, for example, a use after free scenario, things like that. So it's a trade-off. You do have your memory allocation managed by something that works and is safe and secure. You lose some throughput. You introduce some potentially unpredictable latency into your system, but at the same time, you don't have to deal with a huge swath of potentially very, very problematic memory issues and security issues.
I thank you very much. That's a good point. I have also some commentary from Łukasz. Did you, Przemek, watch yesterday presentation?
Just briefly. I had to look at the structure. No.
Okay, but I have a question. I think that you can totally answer that. At which step of examining performance issues we should dive into garbage collector? What's your opinion? What's your experience with that?
What we do is we periodically run this stress test under JFR. JFR is the Java Flight Recorder, which basically is a low impact data collection framework within JVM. We collect all data related to method. So it samples threads, sees which methods take up a lot of time. Also takes some garbage collector statistics. And then we look at them, and if we find that there are issues with memory allocation, we try to have a look at it. And yes, for example, Jira does have a bit some unsolved memory churn issues. It has gotten better recently with the advent of Java 8 and newer Lucene, but we still have some things to iron out. Now, the problem is that these aren't really that easy to fix. So yeah, the answer is you should have a look at it periodically, preferably under stress loads that mimic your customer data and load scenarios. Whether you will be able to act upon this data is a separate story, because if it's a complicated third-party library that introduces high memory churn, you may be out of luck, and maybe it actually needs that churn to work. But you may, strike gold, and it may turn out that you introduced accidentally high memory churn, and you may get away with some thread local caching or some big object pooling, or maybe even some garbage collector tuning to fine-tune the performance of the GPU.
I have a good follow-up. You're asking really good questions. I have a good follow-up for this from Marcin Kwiatkowski. Can you list 3 techniques that you follow in everyday routing in order not to have those memory problems? Do you check the memory complexity every time? Do you use some Java tweaks or things like that?
We don't really. So if we spot anything in the pull request phase, we would typically run a performance test, because we have JPE available, so we can see how the memory consumption looks like. But in the end, I think a more important thing to look at is the overall throughput of the application. So if it degrades because of memory allocation, it's obvious that you have a big problem. If you just have a bigger memory allocation, but it looks like garbage collector is coping with that fine, because these are short-lived objects that do not get out of the young generation, are now very efficiently swept out, then you don't really have to worry about it, I would say. But what is very important, what is extremely important, is to have some kind of performance testing in place for your application to make sure that you don't introduce regressions. And
a question about how to do a performance testing and what to use, because a lot of time we might get biased by the hardware or by some optimization which is done by hardware, so it will behave totally different on hardware A and on hardware B. How to get a reliable and measurable results?
Yeah. So what we did was for our data center products, which are again cluster products, we've measured. So we set ourselves targets. We said, okay, so this is the data size we'll be working with. These are our target goals for performance. And we had a look at how various kinds of hardware affect that. And we relied on Amazon, because that's the simplest way of getting hardware nowadays. And we, basically established a set of recommendations and said, okay, this type of instance at this size seems to be the best in terms of price performance ratio within all these boundary conditions that we set out at the beginning. So we have this kind of documentation available online for our customers to consume. And that's basically how we approach this problem. In general, it's very hard to make general recommendations. For example, what we did was we tried to find out whether how does local I/O influence your your instance. So we compared NVMe solid-state drives, which are really fast, like that. These are really, really fast drives. Again, Amazon offers them, with RAM disks. Obviously, RAM disks are not a good idea, not that of a good idea for production. May introduce some resiliency issues, but at least if you compare performance on these two, you can say whether how much of a factor is your local I/O. And so basing on that, we said, okay, if you are running with hardware, local I/O provider hardware with that speed, you don't have to worry about it at all. It's not a factor anymore. Right? So that's another technique. You can factor out certain things out of the variables. I also did that in this presentation, right? I tried to limit the amount of variables by saying, okay, we'll only look at throughput. We won't be releasing memory back to the operating system, things like that. So the more you can trim out, and ideally, if it's not a trade-off, so ideally you say, okay, this variable is not important because the better off you are, right? Because the less noise you have. In general, performance testing at scale, especially with end-to-end scenarios, such as the one that we are using with a driver, is very noisy or can be very noisy. So we have to pay special attention to how you set up the environment so that the amount of variables in the end is as low as possible, because in the end, if you hit a regression, you will have to find an answer of what caused that regression. And if you have to look at all the pieces of the puzzle at the same time, it will be pretty much unsolvable.
Yeah, that was also one of the questions Shimon asked. Have you tried to optimize and tune GC automatically, or do you test and check everything manually?
So the only thing I did manually was I applied the default, the suggested options, and did this page size tuning. I didn't manipulate any of other settings that these GCs have. Normally, if you would like to get every single bit of performance out of your garbage collector, you would probably select the ones that perform best in your initial test, and then try to have a look at, with JFR in hand, whether you can increase the application throughput or reduce the post times a bit, depending, again, on what your end goal is, predictability or throughput. So,
and about testing, could you also share with us, because Martin he's not believing, I think. Did he heard correctly that we have a memory consumption test on CI?
We don't have a memory consumption test on CI, strictly speaking. We have tests that run performance regression testing between release to release, and also in constant CI loop. And you can enable flight recorder on them. That will have a tiny bit of an overhead. In our measurements, it's like 1-2%. And then you can have actual artifacts with data about garbage collection in the CI loop as well. But we are not, as far as I know, we are not actively consuming those. So we are not, we don't have a specific CI loop for that. We just look at them on case-by-case basis if we want to, see whether we can improve performance. But in general, if you look at throughput, you can, and you're like within 95, 97 range of throughput, you can just sometimes say, hey, okay, that's fine. We don't need to tune it more, because we would spend potentially enable some risky, not as well tested settings, and gain 1 percentage point of performance, right? So, for example, personally, after what I went through with all this testing in a couple of past days, at least on this specific kernel that I was using for testing, which is again 4.14, I wouldn't be recommending enabling on production system large memory pages, because like within let's say 20 restarts, I hit a really breaking bug that required to restart the whole cluster. So you always have, but the bottom line is you always have to look at what you can gain possibly, and then see whether you want to spend the time tuning. And I guess throughput and post time, depending on priority, on the goal, is a good place to start.
I think that that also fulfills the question from Eugeniusz about if you were to choose one for all applications, it should be parallel or not. So I think that fulfills that also.
It's more complicated. So from the testing that I've shown you, it seems like ParallelGC was winning for Jira. Now the problem is that I'm really worried about why I had these discrepancies, why it sometimes came out at the bottom. I expect that, and I will definitely look into that, because we have to ship certain recommendations to our customers. And if ParallelGC is the fastest, we should be recommending that. If it's not, we should be shipping G1 or some other one, right? So I definitely want to get to the bottom of this. I suspect there's some kind of problem with limping node, where one of the nodes was actually performing much worse, the other was performing at usual performance. That caused the performance degradation with ParallelGC. But at this point, I have no idea what was happening there. So that's a bit worrying. But in general, people are using the default GCs, and as I said, probably between 80 and 90% of our customers use Parallel, and these are large-scale installations, and the rest uses G1. So these both work. There are no critical problems at scale with either of those. So you should technically be able to switch between them without any problems.
Cool. I think that we have one big elephant in the room. Bartłomiej Strudzik asked about it. Do you consider migrating some parts of Jira to some other technology than Java because of the performance issues or GC issues?
Not for these reasons. I don't think so. So we may consider some other technologies. We've dabbled in Scala in the past. We have some Kotlin code, but the reasons for all these tech stack decisions was never performance or garbage collection performance, even more specifically. It was always ease of use, developer productivity. And in the end, if you look at the guiding principles of Java versus C++, especially 20 years ago, this was always about this. So this decision that the world really undertook to migrate from C++ to Java for a lot of large projects, or majority of large projects, was always about developer productivity, not so much about performance.
You reminded me one of the first questions which was asked on our webinar from Łukasz, who's a C++ and Python dev. When GC really matters, should we bother for some simple apps? I know that we're talking about it all the time, but what about some simple apps? I know the simple app is not very strict description, but after which scale or maybe complexity level we should consider taking care of the GC?
Mm-hmm. At the point where you start thinking that maybe you need performance testing now. So a simple app typically doesn't need that, and especially so that was maybe a bit of a cheeky answer. A more concrete answer would be: it's really easy to write to test or run your simple app, even on production. We have a large database vendor who actually ran JFRs on their production and gave the results to us. And you can run it, you can collect the data, and you can have a look at the garbage collector characteristics. And again, if they are in the 90% category range, it probably doesn't mean that you need to look at garbage collection from throughput reasons. If it's a simple app, chances are you are not really that worried about latency. So that's basically it, right? You can run JFRs, have a look at what they say, what Mission Control says about the log file that you've acquired, and make your decisions based on that.
Yeah, I think that until you're writing some kind of a proxy, but if you're doing a simple proxy, maybe Java is not the best choice.
Maybe it should be C++.
Let's not jump into this, but
yeah, a bit of a funny story about C++ is actually maybe surprising, but memory allocation in C++, at least the heap allocation, heap-based allocation, is slower than in Java. Maybe surprising, but not until you realize that Java doesn't actually allocate memory from the operating system. Especially in my tests, it already had this 40 gigs of RAM, and just said, okay, I'll place this object here, this object there, right? So there was no penalty where you would have to go to the operating system and say, hey, I want 10 megs more. And C++, when it does, at least with the standard allocators, because C++ is an awesome language, you can substitute your own allocators, will go to the operating system, and this call takes time. So if you were to do some micro benchmarking around it, you would find out that C++ would be slower. But obviously, C++ has specific allocators. You can also allocate memory on stack, which is then super fast, just like in Java. So, yeah.
I have, I think, two more questions for you. One from Detek. I think that's how I should pronounce it. Do you know an example of a company having a product so sophisticated / complex that they wrote their own GC? Or does everyone just tune the existing ones and it's enough?
No, but I know
Red Hat is a good example.
Yeah, I don't think that was the reason why they did that. So I don't know of anyone who wrote their own GC. I know about companies who spent a lot of money, either on consultant work, where consultants would tune their garbage collector, because that's really the easiest. And if you're in such a situation, it's the easiest and the best way of getting your garbage collector tuned. Or spend a lot of money training their employees. Their training was delivered then by the consultants to understand how garbage collection works, how you can tune it, because that's really what you should do. You should not be writing your own garbage collector. Well, maybe for some embedded reasons, right? So it wouldn't be a sophisticated application. It would be a sophisticated use case. Maybe the application would be rather small, but it would be traveling to Mars and can't afford garbage collection, and then you would be writing something which would be super simple, maybe just for a use case. But that's pure speculation.
Yeah, for the use case or related with the hardware that you have and stuff like that. Makes sense. And one last question: what is the main thing that we should get from this presentation? If you could put it in a nice summary.
Just one thing. It's worth looking at how your garbage collection performs. If I were to list just one thing, because as you've seen from my graphs, there are real life differences between production ready garbage collection algorithms. If I were to choose a second one, test ParallelGC versus G1 and see which one offers you better performance.
Okay, thank you very much. It's 9 p.m. so I think it's a good moment to cut our novel Q&A. By the way, email address jww@spartest.com works again. Sorry for that. We fixed that nasty bug in the middle of the webinar. And thank you very much for today. It was the fifth of 5 days for this webinar week. So 2 more days to go and 2 more presentations to go. Tomorrow you'll meet with Maciek Przepióra one more time. This time Maciek will speak about effective work from home. And on Friday you'll meet with Alek Mierzwicki, and Alek's presentation will be from Java coder to cloud developer. And on on Monday, you had a lot of questions about the cloud solutions in Atlassian. So he is the man. He is the man you're looking for. There will be a good opportunity to ask Alec on Friday. And all events starts at 8 p.m. set time. So thank you very much one more time. Thank you very much, Przemek.
Yeah,
and
thank you.
See you at the next webinar, guys.
See you.
Bye.